Welcome to this particular module. If you remember in last class we were discussing about the fabrication or process flow for fabricating the piezoresistive microcantilever, right. And what we have seen that for designing or fabricating such a sensor, such a cantilever, we need to start with silicon on insulator, that is called SOI wafer, right. We also seen that how you can open the window, you can diffuse the P plus first, then you can diffuse P plus plus followed by the metal contact and followed by the front to back alignment and then DRI, right. So, if you see the screen, this is what we were talking about, that in the last module we have seen this process flow in detail. Then we have also seen that if we want to understand the properties of the tissue. So, what happens is when the tissue is out, right, tissue is out, this is taken out with a needle, and this process is biopsy. So, it is called biopsy needle. Then this tissue is sliced into thin slices with a technique called microtome, or with the equipment called microtome. Alright. So, once the tissue is sliced, then different biomarkers are tested, right. It can be estrogen biomarker, it can be prostrogen biomarkers, it can be SMA biomarkers, right, is SMA brown, it is HNE staining. So, lot of various possibilities are there. Okay. Now, if I get these slices of tissue, since these are all uniform slices, assuming do not worry about the figure, assuming this all these slices 1, 2, 3 and 4 are uniform in terms of thickness, right, and one more slice I get for my experiments, which is I will take my piezoresistor and then there is a SU 8 tip, and I will indent this on this particular tissue. I will indent my piezoresistive microcantilever, right, cantilever, onto this tissue, and this cantilever will bend, it will deform or bend depending on the tissue properties. If the tissue is hard, the bending will be less. If the tissue is soft, if the tissue is hard, bending will be more. If the tissue is soft, bending will be less. What does that mean? That if I have a tissue on which I am indenting my piezoresistive microcantilever, if the tissue is hard or stiff, then my piezoresistor will bend more, right. When it touches the tissue, is not it. So, if I just bring the tissue close by, when it touches the tissue, it will bend more, because this particular tissue is stiffer. But if the tissue is not stiff, then my cantilever will not bend much, right. This is less stiff compared to the first case. Less stiff is more elastic, right. So, then my piezoresistor cantilever will not bend. Now, what I am saying, it has a piezoresistor embedded onto the silicon wafer using this particular process flow. That means that if I have the bending of the cantilever, then there is a change in the resistance. Depending on how much the cantilever bends, my resistance would be more or less, right. So, this study would help us to understand the elasticity of the tissue, right, and that is why these are all the tissue slices you can see here using microtome, and then We also discussed last time that the C stands for cancer, E stands for epithelial, B stands for benign, E stands for epithelial, C stands for cancer, S stands for stromal, B stands for benign, S stands for stromal. So, benign stromal, benign epithelial, cancer stromal, cancer epithelial from patient 1 to patient 8. When we have this such a data, and if I indent my this piezoresistor cantilever as shown in this particular figure, right, then depending on the elasticity my piezoresistor cantilever will bend, and when it bends I can know the resistance and convert it to a voltage depending, and then from that we can understand what is the elasticity. This is a inverted microscope, there is a eyepiece and then there is a XY stage. We have used Nikon. MP285 is a micro manipulator, so you can indent the tissue with micron precision. There is an effector, and if you see the piezoresistive cantilever will look like this if you properly fabricate it. If you miss a step, for example, in this particular step process flow, we have seen that there is a silicon nitride that we are using, right. The silicon nitride will work as a counter stress when we use silicon dioxide. If I do not use silicon nitride, then you can see that the cantilever is bent, right. So, there is a compression in the cantilever. This compression can be taken care of if I use silicon nitride. In this case I deliberately have not used silicon nitride, and that is why you can see that cantilever is having more stress because of the silicon dioxide. But in this case I have used silicon nitride as well as silicon dioxide, and that is why the stress is being countered by the silicon nitride. Alright. Now, there is a SU8 tip, and this cantilever is such that this is a back side. So, this side is here in the top and the SU8 is touching this tissue. This is a breast tissue slice, and this is how the individual chips looks like, right. And when we perform scanning electron microscopy to understand the structure of the tissue, then what we found is when we go for FESEM, FESEM stands for field electron, field emission scanning electron microscopy, FESEM. Alright. When we perform FESEM of this particular slice of the tissue which is taken from the breast, then we find that the normal tissues would have a much more smoother surface compared to the cancerous tissue. Cancerous tissue would be much more coarser. So, when we indent the tissue, there is a change in resistance, and if I just connect this resistor, there is a piezo resistor, right. So, if I just connect the resistor in a potential divider circuit, what will I have? If I apply 5 volts, if this is the RS, right, sensor, and this is the resistor which is a fixed resistor, here when R equals to RS, my output voltage VO would be 2.5 volts, correct. Now, if my resistance of the piezo resistor, this is RS is piezo resistor, when the resistance of the piezo resistor changes depending on the elasticity of the tissue, I will have a change in voltage, and that is why you can see here the sensor voltage changes for the type of tissue. Here you can very clearly delineate the benign tissues which are this group of tissues compared to the cancerous tissues which are this group of tissues. So, you can see that benign epithelial has a different elasticity compared to the cancer epithelial. Same way you can see that the benign stromal has a different value compared to cancer stromal. Here again if you compare another patient, we just taken 2 examples, so you can understand. You can see that the benign would have a different value compared to the cancer epithelial, and here the benign stromal will have a different value than cancer stromal. So, the point is that when I indent this tissue, I can clearly delineate the elasticity of the tissue based on the plot and based on the data that we obtained. Here is just a change in sensor voltage as you keep on indenting or when you go further, and you can understand the change in the voltage. Also these are the IHC studies, which is immunohistochemistry, and you can see here HNE, P63 brown, SMA red, estrogen and prostrogen markers. Okay. So, moving forward, once we know the know that piezoresistive microcantilever can help us to understand the elasticity of the tissue, we want to understand the electrical property of tissue. Now, why we want to understand electrical property? Because what we found, like I said, that in FESEM the normal tissues were having a different surface properties compared to the cancerous tissues, or in another case the normal tissue, another way, normal tissues are much more coarser compared to cancerous tissue, or it is opposite, the normal tissues are much more rougher compared to the cancerous tissues. This is also not a correct statement. So, one more statement for you: normal tissues are much more smooth, alright, smooth compared to cancerous tissues. So, normal tissues are smooth and cancerous tissues are rough. When you see this in the FESEM, then what you understand? One is of course smooth and rough and elasticity, but smooth and rough will also contribute to smooth and rough. We are talking about the surface, okay, surface of normal tissue and surface of cancerous tissue. So, the smoothness or the roughness of the tissue will also contribute to the resistance, and that is why it is interesting to study what is a change in the electrical properties of tissue as the cancer progresses. So, now for this we have fabricated a micro interdigitated electrodes, and interdigitated electrodes is electrodes which are in this particular format, which you can see on the screen, right. These are all interdigitated electrodes, and as you can see they are not touching each other, right. So, I can measure my electrical property from this particular set of electrodes. Since they are not touching, right now my Z should be infinite, right, in ideally it should be infinite. So, if I place a tissue on this particular interdigitated electrodes, then what will happen? There should be change in the impedance value or resistance value. Why we are talking about impedance is that if I place the tissue, I have to keep the tissue alive, or at least keep the tissue properties intact, and that is why we will create a well in which there will be interdigitated electrodes, and on that there is a tissue in which there is a saline solution or a media that will keep the tissue properties intact, right, media or saline, so that the tissue will not dry up, and then we are measuring impedance. Now, this media and PBS, media or PBS will also contribute to the other properties, that means it will contribute to the double layer capacitance and other properties. It is not as straight as resistance of the tissue. Now, the new term that will come into picture would be impedance of the tissue, and that is why we will measure the impedance of the tissue. If you see the paper, there is a modeling in the paper, in this particular paper, which is in Sensors and Actuators B. So, if I place and you can see here in this schematic, the interdigital electrodes each are having 10 micron width, this is a width, and distance between two electrodes, which is this one, is also 10 microns, 10 micron spacing, 10 microns width, and then on this when you place the tissue, as you can see here, this is a SU8 well. The well is made up of SU8 material, so that you can hold the saline solution or media inside the well. Now, this is a complete 4-inch wafer, where you can see many chips. In fact, you can see 30 chips, 30 chips, where you can perform the experiments. So, you have to perform a frequency sweep from 0, which is DC voltage, to let us say 2 megahertz, and you will find out the change in the impedance as well as the phase of if I place normal tissue and then cancerous tissue. So, you can see here there is a change in the impedance, and for normal tissues compared to when you look at the cancerous tissues, we have also compared that if you have 10 micron spacing or 30 micron spacing, what is the change, but what you need to focus here is that the y axis. So, if you see the y axis, what you will find out in both the cases, that is benign and cancer, that the impedance for benign is different than impedance of the cancerous tissues, right. You can here very clearly see that. So, the point is, can I use electrical properties to delineate normal and cancer, like I was using in earlier cases mechanical properties, which are elasticity. So, now we can, in a way we can understand that the mechanical properties, which is the elasticity of the tissue, and the electrical properties, which are the impedance of the tissue, can be used for delineating, that is distinguishing the normal or benign and cancerous tissues. Okay. So, if I want to understand how can I fabricate such kind of electrodes, it is very easy. You take a glass substrate, then you deposit a gold film. Now, I told you earlier also, whenever you want to deposit gold film, you have to have the chromium as a base material, because chromium will help in a better addition of gold. So, I have a chrome gold. After chrome gold, I can pattern these electrodes with a very simple process called photolithography. So, I have a glass, I have here chrome gold, let us say this is chrome gold, this is my glass. On this I will spin coat photoresist, right. I will spin coat photoresist, assuming that let us say it is a positive photoresist, PR. Then next step would be soft bake, right, soft bake 90 degree centigrade, 1 minute, hot plate, followed by loading a mask, So, my mask would have this particular pattern. And this will be my bright field mask. So, this is my bright field mask. After this mask, I will expose this wafer with UV lithography or UV rays followed by developing photoresist. Once I develop the photoresist, what will I have? I will have my glass wafer with my chrome gold and photoresist left in the area which was not exposed by UV, since my photoresist is a positive photoresist. So, the characteristics of the positive photoresist is that the area which is not exposed will be stronger. The area which is not exposed will be stronger. So, this is my positive photoresist. All right. After this, I will go for hard bake. Hard bake. Hard bake is done at 120 degree centigrade for 1 minute on hot plate, followed by dipping this wafer in chrome gold etchant. So, if I dip this wafer in chrome gold etchant, then what will happen? I will have my glass wafer and my chrome gold protected by the photoresist like this, is not it? It is very easy, right? Steps, process flow. Once you understand process flow, it becomes very easy to fabricate any sensor per se. Okay. So, what we have? We have positive photoresist, we have chrome gold and we have glass, correct. After this, I will dip this wafer in acetone. If I dip this wafer in acetone, what will happen? Acetone will strip off the photoresist and I would have this particular pattern. So, this is pattern number in C. Again, let us quickly see once again what we have discussed. We have glass wafer, then we have chrome gold. After we have chrome gold, we have a positive photoresist spin coated on chrome gold, followed by a soft bake, followed by loading a mask, exposing the wafer. Since the positive photoresist and bright field mask are there, whatever the pattern is there on the mask will be pattern on the wafer, that we already know. Another way is that the area which is not exposed will get stronger, and that is why after the performing the UV lithography, if I develop this photoresist, or after performing the UV exposure, if I develop this wafer, develop the photoresist in a photoresist developer, what will I have? I will have this particular wafer where the photoresist in the area which was not exposed by UV will get stronger, and the photoresist where it was exposed by UV will get weaker, followed by I will put this or dip this wafer in a chrome gold etchant. When I dip this wafer in chrome gold etchant, the chrome and gold will get etched and the photoresist will be still there, which now what I will do is I will dip this wafer in acetone. Acetone is a photoresist stripper, and when it strips the photoresist, then what will happen? We will have this particular pattern which is shown in C. Okay. Now, after that what we want? We want this interdigitated electrodes to be inside a SU 8 well, is not it? So, what we will do is, now after this I will take this wafer which is my which is shown in schematic C. I will take this wafer like this, alright, and on this we will spin coat SU8, we will spin coat SU8. So, if I spin coat SU8, right, this is SU8. On the interdigitated electrodes, then I will perform soft bake. Now, in case of SU8, the soft bake is done at 65 degree centigrade and the time depends on the thickness of the SU8 material, alright. If the SU8 is thicker, the time is more, if the SU8 is thinner, the time is less. So, after soft bake, I will perform exposure, and exposure, that means we have a mask, and SU8 will act as a negative photoresist. That means the area which is not exposed will get weaker, the area which is not exposed will get weaker. So, I have this area, I will have this area, correct. So, what I will do is I will have a mask, this is my mask, and the area which is not exposed is this one, this one and this one. You are getting it? Now, if I use such a mask, what will happen? SU8 is a negative photoresist. Okay. So, if I use mask like this and then expose the wafer, followed by hard bake. In this case, after exposing, you have to go for hard bake, not like other kind of photoresist, and hard bake is done as 95 degree centigrade. Again, the time depends on the thickness of photoresist, followed by photoresist developer. That is the difference between SU8 photoresist and other photoresist. Then in other photoresist, we go for soft bake at 90 degree, followed by loading the mask, exposure, developer, hard bake. But in this case, we are going for soft bake, then exposure, then hard bake, then photoresist developer. And when you develop the photoresist, because the area which is not exposed, SU8 is negative photoresist. So, area which is not exposed with UV light will get weaker, and that is why after developing with photoresist developer, the pattern will look like schematic number E, right. You can see here the area which was not exposed, the photoresist got developed, and then if you want to make the material harder, which is photoresist, you want to make it harder, you can further bake it at 125 degree centigrade for some time, right. Again depending on the type of the photoresist, or depending on the type of the thickness of the SU8 that you are using. Once you do that, what you have is that you have your interdigitated electrodes inside the SU8 well, and now your chip is ready for testing the electrical properties of the cancerous and the normal tissues. Now, we are talking about breast cancer, but you can talk about any tissue related cancer in this particular case. If I load the tissue on this, right, if I load with some saline solution or media, I can measure the impedance of this particular tissue, right, across the terminals. right. So, this is how you are measuring the, or this is how you can measure the electrical properties of the tissues. So, since we have learned electrical properties and we have learned the mechanical properties of tissue, the next step would be to understand the electromechanical properties of the tissue. Now, we have done individual mechanical properties, which is the stiffness, and we have also tried to understand the electrical properties, which is the impedance. How about we see both the parameters together, that is electrical and mechanical parameters together. So, that we will see in the next module. For this module, just understand this much things. In the next module, what we will discuss is how can you design a flexible sensor that can perform both electrical and mechanical studies together, or phenotyping of tissues electrical and mechanical simultaneously, right. So, till then you have any questions, please ask me, ask my teaching assistants. There is a forum, right. You have to solve questions by yourself, you cannot ask the solutions to the question of the assignment. The forum is to ask doubts if you have any, do not ask for the new ideas, okay. This is doubts from the topics that I am teaching you, right. You can you are free to ask anything from the course content, and next module, let us see how can we fabricate a sensor which is flexible in nature and can also measure both the properties electrical and mechanical simultaneously. Till then, you take care, have a nice day,